Now in this video, we're going to be learning about a new process called trigonometric substitution. And there are 5 integrals that I've written here on the board. And your first thought whenever you see something that has a function inside a square root, as all of these do, might be to try u substitution, which would be a good instinct. But remember, in order for u substitution to work, the derivative of what's inside needs to be able to cancel with something that's on the outside, or you have to be able to do a back substitution. And the only one of these 5 that would actually work out nicely if we tried to do a u substitution is this one. And if you look at it, you can tell why. The derivative of 1 minus x squared, which is the inside function, would be negative 2x, and that would cancel out with a 6x that's sitting there, and leave me with just a nice constant that I can pull out. So this is a u substitution problem. But if you look at any of the others, that's not going to happen. And you can pause the video here and think more about that if you'd like. So whenever you see something like this, and you have a square root of sum or a difference, trigonometric substitution is sort of the way you need to go. And trigonometric substitution basically consists of replacing the x variable that's in here and the dx. It's a form of substitution, but instead of doing u substitution, which is a function that's already in the problem, you're substituting with a specific type of function. Now, the reason for this is that the trigonometric identities include the Pythagorean identities, and the Pythagorean identities can replace the sum or difference of 2 things that are squared with a single squared thing. That would allow us to take something that we cannot take the square root of and replace it with something that we can, therefore getting rid of the square root. So what I'm going to do is walk you through an example. Take the antiderivative of 5 over the square root of 1 plus x squared, and we're going to walk through this example. Now here are the rules for substitution. If you have a square root of a number squared minus x squared, you substitute that number times sine theta. If it's the sum of a number squared and x squared, it's a tangent of theta. And if it's the square root of x squared minus the number squared, it's the number times secant theta. And we'll talk about why that is as we do this example. All right, so I'm going to do a trigonometric substitution here. So the first thing I have to do is figure out which identity and which substitution I want to use. Well, this is a number plus x squared, and if I look at these identities, that matches this middle form. So I'm going to do a substitution that's x equals a, which is that number that's being squared here, the square root of that, which this is 1, so the square root of 1 is 1, times tangent of theta. Now, when you do a substitution, whether it's u substitution or trig substitution, you always have to replace not only the variable, but the d variable, the differential there. So I'm going to find the derivative in order to get the differential. And the derivative of tangent is secant squared. And that means that dx is secant squared of theta times d theta. Okay? So now I'm going to do the substitution part. I'm going to replace the x in this integral with tangent theta and the dx in this integral with secant squared theta d theta. So that'll look like this. The integral of 5, instead of dx, we write secant squared theta d theta over the square root of 1 plus tangent of theta squared. So tangent squared theta. Now, this thing is entirely in terms of secant, so now we're in the process of wanting to simplify this. Well, the nice thing about this substitution is if I replace this with tangent, I get 1 plus tangent squared, which is a Pythagorean identity. 1 plus tangent squared is secant squared. These substitutions will always yield Pythagorean identities underneath that square root, so you can replace it with a single squared term. So this is now 5 secant squared theta d theta over the square root of secant squared of theta. And now the square root of secant squared is secant. And then the secant that's on the bottom would cancel with one of the secants that's on the top, which would leave me with 5 secant theta d theta. So now this is something I can take the antiderivative of because I know the antiderivative of secant. It's 5 times the ln of the absolute value of secant theta plus tangent theta. And I'd probably go ahead and add the plus c here. Now, this is in terms of theta. We want it in terms of x. So in order to remember what to do with that, we have to go back to our original statement of what x was and use that to get what theta is. So theta is the inverse tangent of x. And what I'm about to do will look remarkably familiar to you. If you remember when we took the derivatives of the inverse trig functions, we ended up doing an implicit differentiation, and then we ended up drawing a triangle in order to get everything to the terms we needed. I'm going to be doing the same thing here. So I'm going to draw a triangle that represents that theta. It's a right triangle because all trig is based upon right triangles. Theta, I always put it there. It's just my thing. And this is inverse tangent. And inverse tangent takes in a ratio of opposite over adjacent, and this is x over 1. So the opposite side of my triangle is x, and the adjacent side is 1. That allows me to calculate the hypotenuse, which would be the square root of 1 plus x squared. Now, if that looks familiar, it should. It should match the square root that you had in the original antiderivative. And if you remember, when you take the derivative of a square root, it often ends up with a square root in it that's the same stuff anyway. So this always should happen. So now I'm going to find what secant of theta and tangent of theta are based on this triangle. So I've got 5 times the natural log of the absolute value of secant is hypotenuse over adjacent. So that's the square root of 1 plus x squared. And then tangent is opposite over adjacent, so that's x over 1. And that is the antiderivative of what we started with. That's trig substitution. So I'm going to do a couple more examples in other videos, and you can watch those and learn how those substitutions work.